Welcome, everybody, to the PyMC Labs webinar today with Ulf Aslak. I actually met Ulf when he showed up on the PyMC discourse and was like, "Hey, I just built this cool GPT bot for PyMC." I was like, "It's amazing. I gotta meet this guy." So now, a couple of months later, we are here. And Ulf has done a lot of work with PyMC Labs and amazing contributions to PyMC Marketing and the PyMC ecosystem as a whole. So very excited to have him talk about time-varying coefficients, time-varying intercepts for the MMMs. And that's something that is like really state of the art. So really excited about that work. A lot of that is going to go into PyMC Marketing. So yeah, Ulf, thanks so much for joining today.
Thank you so much for having me. I'm super excited to do this. I saw my first PyMC Labs webinar like a half year ago, and I was like, "That's awesome. These guys are super cool." So now I'm pretty excited to be in the hot chair. I should just introduce myself. So my name is Ulf, and I have a background in physics and applied mathematics, PhD in complex systems, and then I've worked in marketing for some 2.5 years maybe now, maybe more. It's hard to count. And yeah, Thomas just explained how I started working with labs. Yeah, that's me. I'm based in Denmark. I'm in the coastal city of Gilleleje right now, looking out at the ocean. So if I get distracted, it's because it's a beautiful day. Yeah.
Beautiful. So one thing that I always love to ask people is why are you a Bayesian? What do you think is cool about it? Or what was initially appealing?
Yeah. Yeah, so I think it would actually be like false calling me a Bayesian, because I think I'm more of like I've dabbled in like a lot of different domains of computer science and like applied maths, and I've always been attracted to the toolbox that solved the problem the best. So I think I'm very pragmatic when it comes to like approaches, and I'm definitely not like a Puritan Bayesian. Like I could definitely see myself using a frequentist toolbox if like the data set was enormous and it didn't make sense to have incredible intervals in my coefficients anyway. And so why I love the Bayesian framework right now is because I do a lot of work with marketing, and in marketing, like there's just a lot of like well, for example, you have highly correlated variables. In that case, it's really nice to be able to set priors on those variables when you fit the model, because maybe you know something about these variables. That becomes a little hard to do with frequentist methods. Not that you can't, like you can set constraints in your optimizers and stuff, but it very quickly gets very unprincipled and dirty. So I like this like principled approach to modeling, problems where the data isn't enormous, and you would otherwise have to do just a bunch of hacks in order to get it to work well. With the Bayesian method, you can do it in a very nice and principled way. So yeah.
Yeah, I love everything about that. It's a very useful tool for many problems, not all problems. Yeah, I guess also welcome everyone to everyone who joined. Really excited to have you all here. We're gonna do a quick presentation. Feel free to put your questions in the Q&A, and either during or after we'll get to them. But yeah, without further delay, Ulf, feel free to go ahead.
Yes. Thank you. Right. So there we go. All right, so the presentation I'll give is called Time Varying Coefficients in PyMC Marketing. What I will try to communicate is like why time varying coefficients are in fact like an important component of all marketing mix models. I'll try to build like an intuitive example that explains why this is the case, and also like spend a little time talking about how I encountered the problem. So basically building marketing mix models and observing like the lack of time varying coefficients and what that did to the performance of the model. That will be the premise. And then afterwards, I'll showcase the notebook that we've built to demonstrate the use of time varying coefficients in PyMC Marketing, and try to make it as accessible to the viewer. So like after you've seen this, you know where to go and like what notebook to run to start like playing around with this yourself. Before all of that, I will just like quickly tease or like reiterate on what PyMC Marketing is, because there may be viewers in the audience.
Ulf, I think you're in, at least for me, you're like in the wrong view where like we see both slides.
Oh, that's
so
important. Okay, yeah, there you go. New share. And then we go here. Better?
nope, nothing changed.
Oh, wait, I have to click share. Better?
Yes, okay, that's perfect.
Nice. Thank you. Sorry about that. Yeah, so PyMC Marketing, for those that haven't used it or are interested in like a quick brush up, it's a marketing analytics library. It's implemented in Python. So you can import it in your Python code, and you can basically go ahead and set up a marketing mix model in a very straightforward way. It's open source, and I think that's like, I'll just meditate on that for a half minute, because I think that's like super awesome. If you think about like the value of the problems that you're solving with marketing mix models, it's pretty incredible that there exists tools that are free. And I'm not going to dunk on anyone, because like Lightweight, MMM, Robin, Orbit, these are also free tools. But we're also going like very far, adding like extra features and things that make this not just like a standard MMM, but an MMM which can handle lift test calibration and budget optimization, and recently also time varying intercept. So I love PyMC Marketing because it solved problems for me where I was at previously, working not within PyMC Labs, but at my previous job. And I love working on it because it's really cool to provide like a lot of value. And we don't know how much value we're providing, like, but it feels like that, at least if like, you know, just one data scientist at one major brand is putting their marketing spend and their revenue data into this model and getting a result, like they've just saved potentially millions of dollars of like expensive consulting, right? And then of course, like we're also a consultancy, so the problems can get increasingly advanced. Like you might have like multiple brands in your portfolio, and then there might be like other things you need to do. But since it's open source, you know, it's accessible, and you could do basically anything you want with it. So it's a really good start if you're building MMMs, or if you're interested in getting a solution with the marketing mix model. So my introduction to this was, I was working at a media buying agency, which is also an analytics partner for brands. So this company is called Precise. They're pretty big in the Nordics, and they're growing. It's really a big company, and they buy, you know, ads for brands, basically, particularly online ads. And if you're doing that, very quickly your customers are going to come to you and they're going to ask you like, well, like how much sales are all these Facebook ads we're buying, like how much sales is that driving? And classically you would answer that question using like a multi-touch attribution model. And over time, like it became harder and harder to rely on the answers from those models, because the multi-touch attribution models, they relied on cookies, right? So you would need to be able to track the user journey across like an extended period of time, across multiple sites, like interactions with multiple ads, in order to say like which ads could be attributed a sale, or to what extent at least. And so marketing mix models very quickly became like a priority for the company, and that was about the time that I joined. So that was basically all I did at Precise. I built marketing mix models, and that was super cool. Like I worked with the greatest team. I don't know if there anyone here listening, but in case you're out there, like I love you guys, miss you. And we built some really cool stuff, but very quickly, we also noticed that even if you control for, seasonality, even if you control for weather and GDP and so on, like your controls and media variables, they won't really explain your sales or the trend in your sales. Like very often you will just see that your model, like it systematically underpredicts in certain time periods, and in other time periods it underpredicts. So it seems like there's something that's driving sales, which you're not modeling. And that made me think like, well, maybe in fact, like, maybe baseline sales are not static. If you're selling sunscreen, obviously it's not, right? Like your baseline sales are highly seasonal. But if you're selling something which can be easily distorted by external events, that's not super easy to control for. So that's clearly a time varying phenomenon. But then also, what about like marketing efficiency, right? ROAS of a given channel. Well, in fact, that should also be time varying, right? Because let's say you're running outdoor ads and you have just like a really rainy summer and no one goes outside. They're not going to really see your outdoor ads. And so the efficiency will be low, right? And you can keep making examples like this, where at some point you just realize, okay, like somehow we need to include variation over time in these coefficients that account for marketing efficiency and also control influence on sales. So I did as any sane person would do. I went online and I Googled like marketing mix model, time varying coefficients. And it turns out I'm not the first one to think about this problem. I stumbled upon the people at PyMC Marketing. So this is basically how I found PyMC Marketing. And I realized like a lot of the stuff that I had already done was done by someone else, which is like, that's awesome in many ways, because that's, first of all, like you realize like, whoa, we did some cool stuff because these guys did the same. But you also learn a lot, right? So I could port some things from PyMC Marketing into our library, and at the time that I discovered PyMC Marketing, like I didn't find what I was looking for. I was looking for like a time varying coefficient implementation, but that was sort of in progress. Like these discussions were being had, and so I participated in that and started making like first comments on some of the pull requests, and then eventually like made my own pull request, and that got merged, and that was sort of like how I got into working with PyMC Marketing. And it was specifically through this problem of time varying coefficients. So what I'll do now is I'll try to come with I'll try to create like, I'll try to build like a marketing mix model live on the screen to motivate the use of time varying parameters and show how it's included in the model mathematically. And it starts with a linear regression, right? Because at the end of the day, like, or at least initially, a marketing mix model is just a linear regression, right? Like you have some sales and then you have some marketing spend. That could be your Facebook marketing spend. And you're trying to find a coefficient that you can multiply with your Facebook spend so that it adds up to your sales, right? That could be something like this, basically. So your predicted sales is your return on ad spend times your spend, right? So this is obviously like not a very good model, but it gets at the core idea of what the marketing mix model is. Like obviously something we're missing here is that probably we would have had some sales even though we didn't spend any money on Facebook ads. So we can add a baseline sales or an intercept, right? This is a linear regression, y equals ax plus b. We've all seen this. And obviously to make it more realistic, like we need to realize that maybe the connection between spending and sales isn't linear. Like if you spend, I don't know, $10 on Facebook ads and you sell for $1,000 of product, spending $20 on Facebook ads is not going to get you twice as many sales, right? Like it might be, I don't know, 1.8 as many sales or even less. So there's a saturation of spend. And the way we handle that in an MMM is just that we pass the spend through a saturation function. So this is something akin to like it could be like a tanh function, or it could be a logistic function or a sigmoid or something like that. There are many transforms that you can use, but it has to be something that changes the spend from something that increases linearly to something that goes up and tapers off. So we fix that, but there's still another problem, because like if you spend money on ads this week, that spend and that investment will still have like a yield next week, maybe even the week after that. In other words, there's like a carryover effect of marketing, right? It sits with people, and then maybe they don't buy immediately when they see the ad, they buy later. So we call this the ad stock effect. Now this is another transformation you add, and now we have this like this equation which matches with the expression above, like it's just a linear regression with variable transforms. It matches pretty well, right? Obviously, like we'll also need to add, you know, a sum here, because like you have multiple channels, obviously. So now you have this classical marketing mix model. This is actually like how I was introduced to MMMs in a blog post somewhere, and then in another blog post somewhere, and I realized, okay, this is just like standard MMM. It's just a linear regression with transforms. Cool. And there's some other minor tricks that I didn't mention here, but at the end of the day, this is like basically classical MMM. But as you can see in this like oversimplified example here, like these media variables don't explain the target. Like they don't explain this variation, the seasonal variation in the target. And yes, we could control with a Fourier basis or temperature or something like that to get it to fit better. But in the real world, it's just not so simple. There are variations that are not explained by your weather or your seasons and so on. And so what we do, and let's start with baseline sales, right? Is that we can say, well, let's assume that baseline sales is not constant over time. Let's assume that in some periods, it just, for whatever reason, you just sell more because of your brand, not because of your levers and whatever. You can like change the discounts and the marketing spend, just because like that period you just sell more. So you can model that with a multiplier, a time varying multiplier. So M of t here is short form for some wiggly function of time, and it can wiggle any which way that it needs to fit the data well, right? And obviously, if it has infinite degrees of freedom, will overfit. So we need to regularize it a little bit. Turns out the right function to use, or at least the function that works really well for us and that we've implemented in PyMC Marketing, is this thing called the Gaussian process. I don't know if you've heard about it, but it is basically like a non-parametric function that you could fit it to anything. And it's fairly slow to fit. So we use a parametric approximation of that called the Hilbert space Gaussian process. And then it's pretty fast. And that's really nice. So that allows us to fit the data, fit the model like this, where you actually capture time varying phenomenon. But as I said earlier, like you can either have time varying intercept, time varying baseline sales, but you might also have time varying effect of marketing over time. So in the same way that you multiply baseline sales with a time varying coefficient, you can now also multiply your ROAS with a time varying coefficient. And there's different ways to do this. Like I think it's wise to have different multipliers for ROAS and baseline sales. And there's more nuance too. Like you could have different multipliers for each channel in your data, right? Or you could have a multiplier on the total marketing contribution. And there's many ways you can do this, but it's an important thing to add to your model, because if you don't, you risk simply just not capturing the inherent time varying nature of your marketing efficiency. So so I hope that made sense. This was like my intuitive introduction to the problem and how you would add it in a marketing mix model. We've implemented both of these in PyMC Marketing. So we both have a toggle for time varying intercept and a toggle for time varying total media contribution. And then the toggle for time varying individual channel media contributions is still work in progress. So so you can wait with excitement until that launches. Yeah, now I will quickly show this notebook that we've made, which will allow you to, let me see, am I sharing the right screen here? Yeah, there we are. So this notebook here is basically an introduction to using time varying parameters with PyMC Marketing. So if you haven't looked at it already, I can go and have a look. There's this static version, which is hosted in our docs, but you can also launch it as a notebook and then actually run the code. And that's what I'm going to show you now, because I think that's maybe more conductive. That at least would give you a better start. But just quickly showing that like the API is really simple, right? You just instantiate your model. Currently, it's named delayed saturated MM. These are variables that you have to add. So you have to say what the date column is. You have to say what the channel column is, what the control column is named. And then if you want a time varying intercept, you just go time varying intercept is true. And if you want a time varying media, you just go time varying media is true. And then that just gets modeled, basically. So this is what the notebook looks like in VS Code. I'll just increase the screen size a little bit. But this is basically code. You can just start running it. It imports some data. You can see that it's situated here in the repository. So if you clone the repository and you go to docs, source, notebooks, MMM, oops, and then MMM TVP example, this is where it's at. And I think this is a good place to start if you want to use this, if you want to start experimenting with this, and then like you can change parameters and see how it behaves. In this notebook, I give a couple different examples for different types of targets. The first type is where the target is like seasonal. So it has like, it displays this yearly seasonality, and we try to predict that. The second example is where you have this upward trend, and we try and see if we can capture that. And then finally, and I think this is where the time varying coefficients really excel, because it would be hard to construct a control variable for this. The third example is where you have unexpected events that impact the target variable, right? So this intercept that we're trying to capture just suddenly drops, and then it suddenly goes up, and then it stays flat, and then it goes up. And so these are different scenarios where we're trying to use this. We're showing how to use this model and like what results to expect. And then finally, and this is the last part of this notebook, and I'll probably refactor this and push a new version in not very long, because this was recently added. Should give credit to Carlos and Will. They did a lot of work on this, and Juan, basically adding the time varying media contribution. And it works really well. Like, here's the fit. So this is this unexpected event target, and it predicts it really well, even out of sample, which I think is awesome. So I think I don't know if this was very short, but then this gives us a lot of time for Q&A. So maybe that's great. We can always go back to this if somebody wants to have discussion about some of the contents of this notebook. But other than that, I think what I wanted to say, I've more or less said. So let's move on.
Great, thank you. So there are some questions in the chat. We've already had some discussions. Yeah, so feel free to put your question in the chat or the Q&A box. So I'm going to read some to you. So one is, can the MT function be modeled with a sum of dummy variables for each time period? This is what I imagine the model time to model time path flexibly.
Where are the questions?
Yeah, in the chat. Basically, the question is, if you had like a whole bunch of binary features for every time point, Would that be a way to model this?
I think so. Yeah, I mean, there's many ways to do this. Like another popular way of implementing this is using the random walk. There's a really, I can't remember the authors. I read this paper a year ago or something like that. But it shows basically how to do this with a random walk, and that, or a Gaussian random walk, and that works really well. Probably what you're suggesting is also possible. Yeah, but I think one thing to
So
keep,
probably you could build such a model, but it would overfit, right? Like you have just a
that's
whole,
exactly,
like a lot of, yeah.
that would be my
So
concern.
some smoothness constraint is probably going to be beneficial to the model.
Yeah, that exactly would be my concern. Because if you allow it like very high degrees of freedom, like obviously like it will just fit to whatever noise is there, right? And you can also do that with the Gaussian process, but you can also control the sort of the wiggliness, allowed wiggliness of the Gaussian process really well, which is why we really like that.
Yeah. One question that I think is really interesting, how would this interact with the yearly seasonality Fourier function? How can we avoid overfitting with this?
Yeah, I think that's a very good question. Because you could do all sorts of stuff with this, right? You can even unpack the model code and like make the time varying multiplier interact with your control variables. We might even add this as a feature in the future. But if I understand your question correctly, like say you both have yearly seasonality or Fourier basis as a control, and then you also have this time varying intercept or media contribution or media effect. I think you should expect the Fourier basis to capture everything which is extremely regular, right? So everything which is as regular as maybe in the examples that I showed, that will be captured by this Fourier basis, because that obviously like correlates very well with that part of the target series. But everything that's wiggly but irregular, if that makes sense, is a really good candidate pattern to fit these time varying coefficients to.
Although in principle, you could also add like a cosine kernel, which would be able to also cover some seasonality. And in that case, you would probably do one or the other. So I guess one of the reasons is also historical, that we didn't have changing intercept before. And so the seasonality with the Fourier features is just like a super easy way of adding it, because you don't even need a new model, right? You just add that to the feature matrix. And yeah, so now that we have that, I mean, I guess there's you could try both, but yeah, there might be actually benefits to incorporating that into the GP, and then you have like one thing that sort of captures it all together. That's like, I guess if we were building a model from scratch, probably we would just like load more into the GP, or what do you think, Ulf?
Yeah. Actually, like it's a good point. So that's what we tend to do. Like the GPs are flexible but regularized well enough that it doesn't make that much sense to have a Fourier basis in there when you're using it. So we just put everything in there, because the Fourier basis at the end of the day is still like, what does that try to capture? It is it is an addition to your baseline, right? And so if you just have a time varying intercept, like that for the cases that I've observed is enough.
Another question. When do you expect to have time varying coefficients for specific channels available?
That's a good question. So actually, it's not available, but it's facilitated by the sort of API for time varying coefficients that we've written. So what that means specifically is we've written a function called time varying prior, and that function takes a dimensions argument, and to add time varying coefficients on individual channels, we simply just add an extra dimension for the channels. So if you're familiar with PyMC, it has this really nice API for like defining dimensions of your data. And that's fully integrated in like the code that we've written to implement these time-varying parameters. So I don't want to give a promise on when this will be when this will be released, but it's at this point like a lot of the heavy lifting has been done, and it's a fairly low-hanging fruit. But I will say that it comes with some. You should be cautious when you do this, because suddenly having tens of GPs in your model might not give you the result that you're hoping for, especially if you don't have like that much signal in your data, which can often be the case in marketing data. It doesn't necessarily predict the target that well. So that is why sometimes we just go for like adding a time-varying multiplier on the total media contribution.
How should we think of time-varying coefficients versus coefficients estimated by a time series model?
Oh, I'm not sure I understand that question.
Yeah, I think like my answer would be, I don't think you should think about them differently. Like, in order to have time-varying coefficients, you need a time series model underneath, right? So that can be a GP, it can be a Gaussian random walk, it can be an AR1 type model, right? Where it's just whatever description you have for that either latent or observed process, you can use anything you want. So that can be a state space model, or what have you.
Yeah,
Or like a BART type model, which is like more random forest. So yeah, there's a lot of flexibility there.
Yeah, that makes sense. Like, I mean, essentially we do like the MMM is a time series model, right? And we do fit the time-varying coefficients in that time series model. So I think there's not a versus here. Yeah.
If you have issues with lack of convergence, that R hat is higher than 1.1, which parameters should you tune on sample, tune, draw, chains?
Oh, that's a very good question. I think actually like when you fit these GPs, they can be parameterized poorly, and that will lead to bad results. And so there are some like rules of thumb on how to parameterize GPs that we've tried to bake into the implementation that we offer. But it's not perfect. And so I'll go a little bit into the mechanics of how these like Hilbert space Gaussian processes work, but you're essentially like generating m number of basis functions. So m is a hyperparameter that you have to set. And if it's infinite, you get something which is identical to a like traditional Gaussian process. If it's 20, you now have 20 basis functions. And now these basis functions, the first one will just be like basically they're like resonance frequencies on a string. So the first one will just be like bump, and the second one will be like an S, and the third one will have more wiggles. And as you go up, you just have like basis functions with more and more, they're more and more like they have more and more periods. And then what you're trying to fit is basically like the linear combination of these basis function that creates the GP you want. That's like the simple way to explain it. And so to parameterize it, you need to choose M. You also need to choose the range of the basis functions, because they can extend outside of your data range. And you also need to set the length scale. So these are 3 parameters which you can play with. There's some discussion of these parameters in the notebook that I showed real quick. So I think that's a good reference for starting. There's also an example actually of a model that doesn't fit very well, and there's a lot of divergences. And then we change the length scale, and it actually fits much better. So I would say go and change the HSGP, the Hilbert space Gaussian process hyperparameters, when you observe like your model becoming very divergent when you suddenly add time varying parameters.
Can time varying media effects be modeled for a selection of media variables to be viable in models with many variables?
I think short answer, yes. We want to facilitate this. This is this is for sure something that would be like useful, right? Because and this is again, like, I mean, why do we choose the Bayesian approach for MMM? Well, it's because we know stuff about like our channel performances and how these behave that we might want to like encode in the model, like, and you know, I think allowing this flexibility is an important thing. So for sure, like, I think this will be a feature you should expect in PyMC marketing in the future.
And can the granularity sensitivity of changes over time be influenced?
With this, how do you interpret this question, Thomas?
So I would say, yeah, through the kernel, you can do all kinds of things, right? Like if you know that your media effectiveness or the intercept is changing slowly, then you have like a long length scale in your kernel, and that will only allow for like gradual changes. If you assume they're faster paced, then choose a shorter length scale. But you can like, I mean, that's really the power of GPs is you can do even crazier things where you say, well, actually, there's a period where you have a lot of variability, and then that like slowly transitions to a period where it's only slowly. So there's a blog post that I'm going to post actually on PyMC.io. There's a notebook on the Mauna Loa CO2 measurements, part 2. And that is written by Bill Engels, who like has done an amazing job just really showcasing like how crazy you can go with kernels. I had no idea, but yeah, so he's basically linking like 2 time series of CO2 measurements. One is like from ice sheet data, and one is from like atmospheric measurements. And they're like on totally different time scales, right? Totally different quality of measurement. But yeah, you can just like construct a kernel that takes all those things into account. So yeah, that's how I would.
Yeah, that makes sense. My mind was a little bit blown when Bill showed me that you can add covariance, like the covariance matrices for length scale, and the GP will just accept that as its covariance. So you can have multiple, you can have a covariance with a long length scale and one with a short one, just add them up and you get a new Python object. You just put that straight into your GP and it works. And it's fascinating. I think that's sort of what you're explaining here, right? So you have 2 phenomena that are happening at different timescales. And so you just have like a covariance for like a length scale, a covariance with a characteristic length scale for each, and then you just add them up and it works.
That's interesting. So what I meant was in different time periods, you have different length scales. But what you're saying is like at the same thing, you have like 2 things going on simultaneously, right? Like one slower changing underlying thing, and then one higher frequency on top of that. That's news to me, so that's really cool. Actually, yeah, it totally makes sense to like have 2 of the same GPs, but like with different length scales, so you add them together and you have both components.
Yeah, I didn't understand. Like I didn't know I didn't know the trick that you just mentioned. So that's cool.
Yeah, there's some mutually beneficial misunderstanding happening. That's awesome.
Very nice. Yeah.
Will there be an example notebook provided in the future that covers optimization with time varying coefficients?
Optimization with time varying coefficients. I wonder if this pertains to something different from the notebook that I showed.
Well, I mean, I guess how would you optimize your media budget under the time varying?
I see. Oh yeah, absolutely. I think so. Yeah, so we're building this for a client. I suppose I can say that. We just can't disclose whom, but this is actually something that we've deployed for clients and very successfully. They're very happy with it. And that's really cool because it also allows you to do forecasting with budget optimization fairly well, right? Because these GPs, these time varying coefficients, they extend into the future, and they can extrapolate fairly well, like even multiple quarters with decent certainty, and so yeah, this is actually work. Yeah, I expect this would also one day make its way into PyMC marketing, but I don't like to make promises about timelines. But this would be really cool, and it's nice to know that there's a demand.
Yeah, and it makes so much sense, right? Especially when you have things like seasonality or linear trends, that these are things that you definitely want to carry forward into the period that you're optimizing for. and yeah, but like the GPs pretty naturally allow you to do that. They will forecast gracefully, and they will also have uncertainty that makes sense, right? So that like the further into the future, the more conservative your marketing planning, your media plan is going to be. So that's sort of an interesting feature that just falls out of this.
For sure.
What are your recommendations and tips for choosing priors for the model?
I think this is like a broader MMM question, right? But I like that question. I think that's this is something that I've thought about a lot. I can tell you what we did. So a lot of the MMMs that I've built in the past were e-commerce MMMs, and most of the media drivers were digital marketing. And in digital marketing, you have if you're using Google Analytics, which I suppose you are if you have if you're on the internet deploying ads, you know what the LNDA ROAS is, or the last known direct attribution sales due to a given channel is, right? Like how many people clicked that ad and converted. And that's a very good reference to use as lower and upper bounds for your priors. This is something that we've deployed with great success at Precis. And I think like this is something that I've never seen anyone else do it. At least not like read someone like boast about it on LinkedIn, but I think someone should steal that idea because it's like it's really powerful, and it gives you just really good guidelines for like what are reasonable ROASs for your channels, given like like how many people click it and convert right away, right? If it's an upper funnel channel, for example, let's say YouTube, and you have an LNDA ROAS of 2, so that is like like considerable amount of people actually click the YouTube ad and convert. Like you can set that as a lower bound because like if you made $1,000 by people clicking that and converting, like it must have had an effect greater than that because people never click YouTube ads, right? So yeah, this is some of my reasoning for setting model priors. And yeah, there's many more tricks, but that's my favorite one.
Yeah. There's also an upcoming blog post on how to use the results of experimentation to set priors cleverly, and then like you're really cooking with gas because you have something that's really informed by like actual lift tests you've done. How can we differentiate between saturation effects and genuine changes in effectiveness when using time varying coefficients? And when are TVPs more appropriate than creating time split independent variables?
Let's see if I can find the question just so I can.
It's in the Q&A.
Where's the Q&A?
While you dig that up, I can give my take. So the two are have different effects on the. Well, I guess no, they do have pretty different effects on how they change the relationship between the sales. So there might be some correlation there between those parameters, but that's the beauty of the Bayesian framework, right? Like it's totally cool to have a model with correlated things, right? Where you can explain the same thing through 2 different ways, and what you'll see is like, well, if I believe this one parameter is higher, then I believe this other parameter is lower. And that's the same here with saturation. So if that is the case, then you will see that in the posterior that like both of those can explain what you're seeing in the data. But in our experience, the 2 are not really that correlated. So I don't think it's a big practical concern.
Yeah, I agree completely with that answer. I don't have much to add.
How do you think about regularization in this context? The HSGP function is non-parametric, which can be quite noisy if you're not comfortable. Have you thought about implementing a random walk?
Yeah, so I think so it's important to establish that it actually is parametric, and so the parameters you can play with are the number of basis functions that it uses to approximate the Gaussian process, and then the range of the basis functions maybe not super important for regularization, but very importantly, the length scale. So if you find that your Gaussian process or your time varying parameter just fits to the noise, you should definitely increase your length scale, or the mean of your length scale prior, basically. So that is the short answer for that. And it's actually nice because that is the single lever that you should use to regularize. It's not like there's a whole ensemble of hyperparameters that you need to experiment with. No, you can just use the length scale. If you like resolution, you can increase the number of basis functions. If you have weird boundary effects, increase the range. That's modeled through this parameter called C. I don't expect anyone to be able to remember that, but for regularizing, I think the length scale prior mean is the lever to use.
And one thing to add is that thinking about Gaussian random walks and GP is something that was helpful to me. And like, well, when should I use one? When should I use the other? Is that actually you can just write a Gaussian random walk as a GP. So you just like have a very particular choice of kernel, and then it becomes a Gaussian random walk. And the kernel you pick is one that has only a correlation between time points that are directly adjacent to each other, right? Because the Gaussian random walk only looks at the last data point you have, while Gaussian processes oftentimes look at more different time points. And that's the reason why when you look at most outputs of GPs that they're smooth, right? Because they take the average of like quite a few data points in that vicinity. And that's why Gaussian random walks are like so jittery and like stock market like, because yeah, they only have a history of one essentially. And yeah, you can write down a kernel that has a history of one and then you get Gaussian random walk. So they're the same, just particular choice of kernel really. The synthetic data you used in each example is informative, but when dealing with real-world data, how can we effectively model the variability and complexity it represents? Any tips?
Yeah, that's a good question. I mean, so first of all, there's in the real world, you're right, like the synthetic data is informative, right? And I've simulated the target from the synthetic data. But yeah, I guess to answer your question, like, I mean, how can we? I mean, it is basically like if the MMM doesn't have any predictive performance, then you can change your parameters or parameterization and so on, but it will show pretty quickly if there is no predictive performance in your model, like there is no signal in the data. Then you can try and simulate a target from the data and see if you can predict that. And if that's possible, then, or if that's not possible, then you know something is wrong with your model. And then you can go back to your model and iterate on that. But if that works and your data doesn't, then yeah, you have a problem.
In essence, what you're describing is the Bayesian workflow, and I think that's the right answer. You start with something simple, like what Ulf showed, right? On the very first, it's like, well, this model is sort of crappy. Now let's but then you just see that it's crappy and you don't know why. So then you just start thinking about it. Well, why could it be crappy? Well, there's this pattern that I'm not catching. Maybe that is due to lack of saturation functions, and then you add that in, and then that makes it a little bit better. So basically, those first couple of slides where you just like kept adding more complexity, like there would probably be considerable time between them if you build something from scratch to like really figure out, well, what are the components? And there's no real automated process to do that. That is really the work of the modeler, and that's why Bayesian modeling isn't as easy as scikit-learn, right? Where you just like sort of punch something in, and usually the hyperparameters work out well enough. You really need to think carefully. You need to experiment a lot, and this is really what we do at PyMC Labs, right? Like we spend months iterating on these models and trying all kinds of things. Then it doesn't converge. Then we figure out why. We reparameterize. We add this thing in. maybe that doesn't help. So it's yeah, it's a process,
Yeah,
an
for
iterative
sure.
and principled process, but it's sometimes a difficult and time-consuming one.
Yeah, there's definitely some discovery to like understanding like or finding like the right structure for your model. I really like to use the leave one out cross validation implementation Arvis. I've just posted like in the chat. It's like what 10 samples, and then you've produced a like an in-sample on in-sample data. You've basically produced an approximation of the leave one out cross validation predictive performance of your model just using your inference data. So if you're building a model in a way where like you're iterating on the model structure, each time you make an iteration, you run that cross validation approximation on your model on your fitted model, and you can see if it improved. That's because otherwise, you might be. And there's many other validation metrics, like you could also go for out of sample performance and stuff like that. But I think that's one of my favorite ones because it's so cheap. It's so easy to use. It computes in like 5 seconds or something.
Something which we sort of already discussed, are coefficient and intercept GPs good for out of sample predictions?
Yeah, I would say they're fairly good actually. It also depends on like the time scale of your data and just the overall variability of like long time scale patterns and stuff. But for the MMM applications that we've seen, like it's not uncommon that you can get pretty good out of sample predictions a year into the future if you have sufficient data and no COVID.
Would time varying coefficients be a viable option to evaluate change of media mix efficiency after adjusting the media mix? So you have your model, you estimate the parameters, but underneath you've been changing the budget allocation essentially. So I mean that is a thing that goes into the right. That's like just the time series you input, and there's changes in the time series you input as your coefficients. I mean that's totally actually that would help, right? Like you need changes in the media mix in order to get good estimates, because otherwise how do you really get samples of different parts of the curve? So the more you adjust that, the better in a way. And actually, it has been the case in quite a few client projects where we didn't have the highest identifiability of parameters. And one of our suggestions was to actually change the budget in like more extreme ways to just see what the influences are, just to like have better parameter estimation. I don't think they actually took us up on it, because that's like a pretty difficult ask from like the data science team to the marketing team to be like, hey, let's do this thing that like we don't expect to actually work, but we just like sort of need to run an experiment. But I mean, in the long run, it does make sense to run these experiments really.
Yeah, definitely. And also for just like media planning, forecasting, scenario planning. Yeah, it's you can. Yeah, I would say it works when you change your media mix, and yeah, even synthetically, right? So you construct synthetic scenarios where the media mix is changed. Of course, like to validate whether it truly works, like you would have to then like really change the media mix and then see if the outcome matches reality. But assuming that there is like change in media mix over time in the data that we model, also for like the real data we model for actual clients, like if it fits well out of sample, the answer to your question is yes.
A question that I'm very excited about: how would you include A/B testing results on channel efficiency into a model for model calibration using time varying coefficients? So that's something that we actually did with like great success. And I think, I mean, to my knowledge, we were the first people to do it in the HelloFresh case study, where they had run lift tests, essentially A/B tests on certain time points, right? And they are obviously providing you really good information, but you only have them sometimes. But that was really powerful for so there we had Gaussian process time-varying parameters for the channel effectiveness parameters. And then you can just, so that's a latent Gaussian process, but you can just add certain observations into that latent Gaussian process. And that is the result of that lift test, is where we said, like, well, actually here we do have a measurement of that otherwise latent inferred process. And you can even add noise, right? Because no experiment is perfect. So the more data points you have for your experiment at that time point, the less variance that will have. But so you can add that into, and that like dramatically improved the fit, which makes sense, right? Because just like inferring something only from like downstream data that like a time-varying process that you don't directly observe, but you have to infer, is difficult and noisy. But if you have even only at brief time points observed this process, that like helps greatly constrain it. So yeah, that can be done. It's not in PyMC marketing yet, but it's definitely something we want to add. First, we need the time-varying marketing effectiveness coefficients. But yeah, we've done that in the past. It works really well. And it's like pretty much the only way you can properly do that with time-varying parameters, because if you don't have time-varying parameters, right, and I mean, if you run lift tests at different time periods, you'll get different results. How do you square that, right?
I'm curious, did you implement that as an addition to the likelihood term of the model, or through some other mechanism?
So in PyMC, it's actually pretty easy to just add that to the GP latent process. Yeah, I don't know from the top of my head how to do it, but like coding wise, it was pretty straightforward. I can pick that up.
Yeah, it's super cool.
Will there be an update of the MMM model to differentiate between upper and lower funnel channels? Great question. What do you recommend starting with to address this issue?
That's a really important question. Actually, Thomas, you have that excellent blog post on the do operator where you basically show how to model first, like what is it like how you should explain it. I love it. I think it's awesome.
Yeah. So actually, I'll just share my screen real quick because that is indeed like exactly the type of things that we're starting to work on, explore at PyMC Labs. Is I mean, generally the vision is we want to open source as much as we can, right, and like set standards there. Because I mean, MMMs are like, I mean, how often can you build the same model without getting bored? Not that often. So we open source that, we make it the best, and then what I think where a lot of the value will come from is moving beyond that, right? And like one of the ways is just to build more, incorporate more things holistically, and that can be different things. So this is that blog post we wrote about it, causal analysis of PyMC, and it has a bunch of like just general things, but the case study we then use is to talk about how you can use this causal framework where you build a structural causal model that has a much richer structure of how the different nodes in your problem connect to each other. So usually most models are like performance spend, marketing spend, influence on sales, right, or impressions or whatever. But I mean, there's so much more, like the price, right? That will definitely influence the how many sales you're doing, right? If you do discount or just lower prices. A model that doesn't have price will attribute that to like, oh, your marketing get more effective. So you're missing things. But the competition price as well, right? If they change their prices, that will have an influence. And then here, so this is like lower funnel. And then you also have upper funnel. So you have brand marketing, which you can assume raises awareness in general, but awareness is also driven by the competition, which does their own brand marketing, right? And then that leads to interest, which leads to considering buying a product, and then to sales. So that's one example of how you can include more upper lower funnel, but you can just imagine going much further with this, right? Where maybe it's not just sales that you want to measure. So one common question in MMMs is, well, do you want to measure impressions or clicks or sales? The answer is, well, ideally all of them, right? Impressions lead to clicks, lead to sales, and in between maybe leads to sign-ons, right? And like to like putting things in the basket. So you just can the more of the business process you include, the further you can push this, the better analysis you can get. Because I mean, marketing will not just have an effect on like the signups, right, or the sales, but will have different effects maybe on like existing customers or new customers. So you want to potentially allow for all of those. So that's, I think, this more holistic view, something that we're really excited about, and something that we're actually getting a lot more interest in, and like people who are like, oh yeah, like this is really the direction we want to take this into. So yeah, I think that's basically the future of MMMs.
Absolutely. And there's, of course, like a huge design problem to be solved in figuring out like an API that facilitates suddenly like all of this different these different demands for what an MMM can do. That's something we're like very much thinking about internally.
Yeah, I think I mean, for the time being, a lot of that will be custom, because that's really where you need that customization. So whether like PyMC Marketing will ever be general enough to where you can like build these advanced models, that will be for the general case. And then if that doesn't fit, then yeah, well, that's the work that we do. So if you think that's interesting, definitely get in touch with us.
Absolutely.
The model includes channel and control parameters. I guess we're also at time. Let me see if there's like one final question that's calibration. Yeah, that the roadmap, that'll probably take some time at first. We need the TimeVarying parameters for the coefficients. Can you share the link? Can the saturation function vary over time? Yeah, so that is what I mean when I say that not just the intercept is varying, but the media effectiveness is varying over time. So yeah, you have the parameters of your saturation function that control like the steepness of that curve. But in principle, I mean, you can have everything vary over time, right? Like if you have an ad stock effect that you think is changing over time, or whatever it is, I mean, that's really then up to the model. I mean, PyMC Marketing doesn't support that level of flexibility, but in principle, yeah, wherever you have a parameter in the model, you can potentially make that time varying.
Yeah, for sure. That's an important point. And I think maybe at some point in the future, we'll have an API which is flexible enough to support any model modification that doesn't like, yeah, we'll have to see about the rigidity of that, but that's work in progress.
Yeah, I mean, one thing that I think will be really interesting, and Will Dean has done really good thinking on this with this new prior class, where right now PyMC Marketing is like very much there's one thing and then like a dictionary to build different models, and that is great and very user friendly. But you can definitely imagine that for more advanced models, you want more fine-grained building blocks, and then it's a matter of, well, okay, how does the MMM break down into these building blocks, and how do we build nice API around that, where you just like can say, well, you have these parameters and they are GP and these are Gaussian random walk, and then you just like plug it together like Lego bricks, not from scratch like with the PyMC model, but the building blocks themselves have some more structure embedded, but you have a lot more flexibility. So that could be cool. We haven't really thought about it too much or figured it out, but it's definitely something that we've been talking about. So that might happen. So with that, well, yeah, I'm so happy that your presentation was brief, because it's like all these questions and discussions which were super useful and fun. So thanks both for taking the time to chat with us and discuss with us, and for everyone who participated in the discussion and asked questions and showed up. Hope you have a great day.
Thank you, everyone. Thanks for hosting me, Thomas. This was super fun.
Thank you. Bye-bye.
Bye.